for the three general presentations, three general sections we just had, we talked about ensembles and particularly two-state ensembles. We talked about this protein A challenge and distributions and continuous distributions. And we talked about hydration of RNA as examples of kind of breaking new areas that CASP is exploring and I think having some impact with. That really involve multiple states and multiple conformations and dynamics, a pretty challenging area. So what we did is that for each of these three areas, I asked the people who coordinated it to put together a list of questions, and you can get a sense of this quickly. Yeah, list of questions. And the questions are rather extensive, and I don't think we can get through all of them. So I'm going to do 10 minutes on each question, and I'll start with the two-state ensembles, 10 minutes on each slide, rather. And what I really want to do then is to, I just read some of the questions and then ask if I can get people either from the front, particularly people up here to comment to keep the discussion going, or the people online, Terry and Bruce and others online, and Creston, et cetera, who are online to comment. But particularly, we'd like to get some audience discussion. So the two-state ensemble, well, I'm going to start with just the first one, just to start, is this appropriate for CASP? Is this something that makes sense for CASP to be doing? Or is it like validation against ground truth is too difficult? And I'm particularly focusing on the two-state stuff that Namita and I presented. By the way, Namita, you should be up here too. So does someone want to comment on that? Is this something we should be doing in CASP, or is it beyond what CASP, scope of CASP? Maybe I can have Bjorn give us his thought about this. Bjorn, what do you think? There's a microphone here.
Yes. If you can get enough examples, of course, but that might be the tricky part, right? You don't have you have two examples and then someone does something and it's hard to say something thereafter. But if it's possible to get the data, it's much, should certainly be done. And also this idea that you have also trying to push that you can test not just against one single, one structure, but actually against the data. Because, you realize when you're actually doing experiments that the models are also a model of the data. So maybe testing directly on data is another way also to put this thing in.
I understand that there was a criticism maybe raised in the proposal of CASP that said something along the lines of, this is not appropriate because you don't have ground truth to assess against. And so yeah, I'd like to hear particularly some negative ideas here. So, I'm joking. I'm just joking. No, please.
That prospectively, there are obviously many examples in the literature. So it's clear, for example, cryptic site open and close, or transporter open and close, GPCR, open and close. So there are really well-defined two-state systems. The question is, before you go to kind of unknown system, to see whether we are able to represent at least with the currently available tools or what modifications are needed to get this done.
Yes, we should be able to validate a test with retrospective data, but also prove it with prospective data. I think Alex made this point yesterday. Let's see some examples where you don't know it's there and you discover it's there and then you validate it's there, right? Yeah.
So that you have to see whether retrospective you can have basically working method. I mean, and if it is the case, then it's absolutely very important for cost.
I have a follow-up comment about that. When we first saw what we called the CDIO, our orientational distribution, and to this date, we have no idea why we see the orientation we do. And so with regards to having more data, I think one thing that we're hoping to be able to do is expand the number of different sequences for our 6-residue linker as much as possible. But of course, this is a pretty work-intensive process to make a new linker, do the molecular biology, express the protein, collect the NMR data. And so we need to be efficient about which sequences we choose to simulate, to do experiments on. And it would be really helpful from the predictor community, the simulator community, to be told in advance of our intensive work what sequences would be most informative. I guess the statisticians call this experimental design, but that's exactly what was just being talked about, was the fact that having some input first from the simulations would actually be very useful to the experimentalists.
And if I can mention another question as well, the problem of linker design is a new frontier in protein design, namely that someone says, what probability density function do they want to have occur in vitro? And then an algorithm or a person designs the linker sequence to achieve that. So the target is a PDF, not a single structure. And in some sense, we're groping towards that by populating that design space with enough mappings from linker sequences to NMR data to continuous models. But if any predictors have insight into the design problem, namely going from a PDF to linker, that is a frontier that's been largely unaddressed that we're very interested in.
And very useful to the biotech community, which is increasingly constructing protein drugs out of nanobodies linked together by linkers. And this is a new frontier in protein-based drug design, and linker design is all part of that.
Yeah, I want to move on to some of the other, one of the other questions. We won't go through all through. No, not yet. So this last question, actually, Namita, you brought this point up. Could task ensemble modeling in the future go beyond two-state representations to include transition states and pathway intermediates? And Bjorn was actually showing not only the two states, but models in between states. How real are those? So, Namita, what are your thoughts about that, and what do you mean by ground truth here?
So I believe that because, in reality, the truth is always beyond the two states, and transition states are kind of really necessary to look at the conformational dynamics and landscaping of it. And so I believe that, the assessment of them is very critical. And in the field of like molecular dynamics simulation, which is primarily what I currently focus on, these kind of things are already being worked on. Especially, we have developed so many enhanced sampling methods, which induce the biases in the system to lead from one state to another state. And if CASP can include these in their, upcoming conferences or in upcoming CASP assessment, this will be really, really necessary and a very good step moving forward.
Does anybody in the audience or online have a thought about this? Alex Bondin, I saw raise his hand.
No, I have another thought about this, because we're, stating what if you don't know? You can also sneak a target where there's only one state in the same competition and see what people come with.
Say that again. You could
you put a target into the ensembles competition, which has only one state,
Yeah.
just to test what people come with.
You know, it's actually pretty hard. We explore that. Even things like BPTI tend to have some alternative states in reality. So, but also there's hallucination that occurs. And I think that's what you're getting at, this hallucination.
Everyone will hallucinate two states because
But we actually, by accident, we did that because we took a, I mean, we didn't create a test set ourselves, but we took a set that contained open and closed states. It's just that the definition of open and closed is different for different people. So so some of these states actually only differ in some side chains, and they didn't move at all when we applied the sampling protocol. So it seems like it's, I mean, you can't distinguish if it should move or not for someone, but yeah.
Wei Zhang, why don't you take this point here? Which developments in computational biology can you imagine that would make an impact in this area? I mean, we're seeing some very nice ideas emerging. Do you have some thought about that?
Sorry, could you explain more about?
Well, just be visionary.
Mhm.
What kind of new ideas might one bring from computer science or from computational biophysics that would impact this?
So I believe currently when we modeling the ensemble targets, we found the dynamic simulation actually is very useful for modeling ensemble targets. But based on the recently released AlphaFold 3 method, I believe actually we tested the ensemble modeling by AlphaFold 3. It's performed pretty good than AlphaFold 2. So we believe the diffusion model should be one direction modeling the ensemble targets in the future. But as we discussed yesterday, I still thinking the data problem is the critical issue prevent us making successful in the ensemble target modeling in this field. But I believe this problem quite critical for the biology field because we already do very good in the static model modeling, like AlphaFold already pretty good in single domain modeling. But in realistic biology, we need the dynamics for the entire molecular. So I think ensemble should be ensemble modeling or ensemble modeling category in class should be very important. No matter for the computation game
Yes,
or,
yes,
or,
yes,
or,
yeah.
or in the realistic biology. Yeah, I believe.
Okay, I think I'd like to hear from a couple of people online. Maybe Faden, you can give us your thoughts. I know you raised, and maybe Creston, if you're still there, maybe you give us some vision on this. So Faden, do you want to go first?
Yeah, so hi everybody. So regarding the how we can use computational biology tools to better navigate protein dynamics, I think we're in a very good place in terms of the developments, particularly the inverse folding algorithms by the Baker Lab, for instance, or the Facebook team that are able to predict what sequence is able to adopt a particular fold. So I think that, using molecular simulations, we have ensemble of structures, and therefore we can find the likelihood of a new sequence in this ensemble. So how does a new sequence shift the probability density of the landscape? And therefore we can then, make some type of targeted optimization that we want to now produce new sequences iteratively that are able to steer the landscape in the direction that we want. So I think this is more like generalizing the inverse folding for molecular dynamics, and this is something that we're working on. I think this is something that is completely possible nowadays.
Nice. And Creston, you want to give us a little vision here?
Yeah, absolutely. I'm of the view, I think if I simplify a little bit, that these kind of multi-state modeling without putting some kind of probabilities on them become borderline meaningless. I think that sort of the extreme is Alexander's point about a single state system, right? If you have a two-state system and one of them has a Boltzmann probability of 10 to the minus 10, right, it's not really very informative. And so saying that two structures exist, of course, they all exist just with some small probability. And so I really think that, unless one puts some kind of weights on them, at least one has to sort of be careful about what it then means. And then, so the reverse of that, I think, is that the more one can benchmark these things against the experimental data, rather than some kind of approximation or interpretation of the data, the safer one is. And I so forward looking, I think that one of the exciting things that a number of people are working on, Phaidon including, is going to cryo-EM data and really not doing class averaging. I think that is probably the most forward way of looking at it, really to validate ensembles against raw images with all the problems that come with that, both computational and algorithmic. But I really think that there one gets around many of these problems. Of course, you introduce new problems, but I think in the longer term, if CAST really wants to have a major impact in the area of dynamics, this is where I would probably focus.
Thank you. Well, I'm going to move on to the next topic, the next presentation topic. Let's go. I need to just advance the slide. And these were questions that were provided by Terry and Bruce and Susan. And I think well, I'll start with the first one, and then I'm going to ask Terry or Bruce to pick out ones they want to get discussed, because we won't hit all of them, and Susan to pick one. But I'll just start with, is the domain linker domain experiment suitable for CASP? I mean, this continuous distribution and disordered region, intrinsically disordered regions, is this outside the scope? Maybe Damiano or Silvio have a thought about this. Does this belong in CASP, or does it belong somewhere else? Damiano here, Silvio's there, I see.
Try this one. Yeah, that looks better. That it is a suitable experiment for CASP. It's of course just one of the cases where you can have a disordered region, because in this case it's constrained, and still we talked about this previously. There are some additional challenges in how you evaluate it, because it may be experimentally underdetermined, so you can end up having very different conformational ensembles which approximate to the same degree the experimental observables you get. So it is, I think, cut this long story short, yes, it is suitable, and it also needs more work in order to come up with the equivalent of the GDTTS or similar measures which are easy to grasp and give you something clear-cut as a result.
Yeah, thank you. Does someone else have a thought about this question about the suitability of these continuous distributions? Either here or online.
So maybe I'm saying I have a thought about it. It's like, I think because previously I worked with disordered proteins, and then I think this question is a little bit different compared to well-folded protein. Well-folded protein, we have crystal structure and it's solved. So we use computational method. No, we know the ground truth and we improved computational method based on ground truth. In this case, the domain linker domain experiments is like, we have experimental data, but we won't be able to fully understand it. We won't be able to interpret or get a really good model from it. So we need to, on one hand, improving our computational method. On the other hand, use those computational methods to solve those experimental data. So it's like growing together. So computationally and experimentally, we are working together to solve a question, trying to get the ground truth. It's not like evaluating computational method with experimental method. But I think this is important questions, because I'm new to CASP. I'm not sure whether it's suitable for CASP, but I think it's important question after we have AlphaFold for solving one domain structure. This definitely has it's meaningful for the biophysics society, but yeah, very suitable for CASP, but I'm not.
What I hear from you is that these methods have to evolve together, the experiment and computation. And I think an open question still, it seems like CASP is a place to do that, but CASP is not really particularly focused on driving experimental methods, I think. But it seems to be perhaps the best venue for doing this kind of thing. I see Andre.
I see that Preston wants to say something.
Oh, you say what?
Preston wants to.
Oh, Preston, go ahead.
Thanks a lot. Yeah, I think that some of this discussion about, is it suitable, is it continuous, is it discrete? I think all of this comes back to the evaluation, right? If the evaluation is against experimental data, people can submit a discrete distribution or continuous distribution or whatever they like. If they can produce a conformational ensemble that fits the experiments, to me, I think that we have no way of saying that that's wrong. And so I think, I think it really depends on whether one does the comparison in 3D space against some ground truth ensemble or representation of the structures, or whether one goes directly to the experimental data. If you go directly to the experimental data, it's up to the submitters to decide whether they think it is more continuous or broad or discrete, rather than predefine it as being one or the other. I think that's a more CASP-like approach, and I think also to be an easier way of benchmarking things that is sort of less biased towards specific interpretations of the data.
So can I make a couple comments about
Terry and Bruce, picking out which points here you really want to get some feedback on? Terry or Bruce, and I see you're making a comment, Terry. I'm sorry I cut you off. You can make the comment at the same time, lead us into the next question.
Sure. But I think to follow up on Creston's point, I think it is important to go to as close to the original observables as possible. And in our case, that's doable. We can back calculate the RDCs from the experimental ensemble. I'll also agree with whoever said that we need populations. I guess that was Creston also. We do need to really be realistic about this. We need the population of each member of the ensemble in order to accurately even do the back calculation of the RDCs. The reason that we show our data, interpret our data in terms of the model that is the CDIO, this thing I've been showing on the disk on spheres, is because it is an approach for taking relatively low information data. I mean, the RDCs don't have that much information in them, and only producing a summary of that information in the form of the mode and variances and covariances of this normal distribution in 3D space. So it's a minimally parameterized model, which I think is important, because if you start building models that and structural models, that is, interpretations of your experimental data that are themselves the basis of some kind of MD-driven molecular refinement, which is the typical approach for doing this, then you don't know what part is your experiment and which part is your ensemble. Okay, I would say,
I
pardon?
still want to comment here, and I want to give him the chance while we're still on the topic, and then.
Yeah,
Sure.
no, was about what you were mentioning earlier about Guy, about CASP and how it can contribute to this. I mean, I think one of the main strength of CASP has been over the years the ability to assess something in an independent way, right? And that requires that you know how to assess it. So what is the ground truth? How do you compare it? And I think one of the challenges in this particular field is exactly to come up with something which is widely shared by the community, because we have been trying to do this in Europe with various experimental methods. And as soon as you bring various different experts into the same room, they start not to agree too much about what is going on. So probably CASP can do the assessment, but there should be something, and I think the SIG is a good starting point in order to generate that consensus, so that the next time you can come with a with something which is strong enough to be evaluated and benchmarked. And that would also give a new lease of life, if you want to say it like that, for the SIG and purpose, beyond having just a presentation. So getting to the actual discussion, we've had that. We've been doing that on a number of topics, especially for IDPs over the last few years. And it really does work, but it requires the effort of putting together the people and getting, if necessary, locking them up in a room until they agree on something. But that is something which you need between the CASPs. Otherwise, you will be stuck with the problem that, again, you have something which works only in certain cases. You may not have so much data, or it may be open for interpretation.
Thank you. I think, Terry, why don't you hit one more point on this list, and then I'll let Susan hit one point. And I want to be sure we have time to talk about the salvation. But why don't you pick one point that you'd like to get some feedback on?
I'll defer to Susan. Let her
Okay,
pose the
Susan.
question she would like.
Pose a question from the list, because we won't do all of them.
Well, one of the things that we see in the small angle X-ray scattering is that it's very difficult to get the conformational variability or explore conformational space. We do that in trajectories right now, but obviously that's limited in exploring conformational space. And so my question was, do CAS rankings to cryo-EM and crystal structures drive the algorithms towards those cryo or high salt conditions, or do you think it's possible that they're able to generate solution conformations? And I put that out to the audience.
Somebody want to try to give a response to that? The degree to which the conditions of crystallography and even cryo-EM bias the structures we see, that's what you're getting at, right?
Yeah. And there is a recent paper in PNAS. I mean, there's a lot of work being done on variability in cryo-EM analysis, but there was a recent paper that showed that even within, if you take those variable models and compare it to what's happening in solution, the solution conformations are more diverse than the cryo-EM.
Okay, I'm going to move then, for the interest of time, to the RNA hydration. Again, more questions than we have answers for. But Rachel, why don't you tell us what of this list you think are particularly things that you'd like to get feedback on, or that community would like to hear more about?
Sure. So these are all kind of more general than just the RNA salvation, just asking about challenges in this in general to try to improve our methods in general. So let's see. I think one question, and this also connects with Susan's a little bit, is what are the advantages and disadvantages of comparing to multiple orthogonal sources? So for example, comparing one score against cryo-EM particle stacks and one SAC score as ground truth in both official assessments such as CASP, as well as in your own self-assessments as you improve your methods. So we'll continue on from Susan and see if anyone has comments or questions about that.
I mean, I'll just respond a little to that, and it relates to the experiment that Bruce and Terry and Susan are doing. Susan actually showed us that she could build an ensemble that would fit the SACS data. And in fact, it's done all the time. Not all the time, but it is actually becoming a more common type of approach, the ensembling fit to the SACS data. But then when she went to an orthogonal set of data, that is the RDC data, it didn't fit. So I think that's a really important observation. And it shows that sometimes, even when we're publishing in good journals and advancing the field with methods that appear to be solid, cross-validation is absolutely critical. And I think that's your point, right? Yeah. And especially with these high degrees of freedom, because with so many degrees of freedom, you can fit things that, there are many ways to fit the same data, unless you have cross-validation or orthogonal methods. I do want to spend a couple more minutes on this slide, and I realize it isn't just hydration, as you say. But Rachel, let me ask, does someone else want to say something else about orthogonal methods of validation? Someone? I see Wei Zhang, you're about to say something. Do you want to say something? Okay. Oh, go ahead, Rachel.
Okay, I can bring up another question. I think with the audience here, it makes sense to ask the question of what information is needed about the experiment for predictors to understand what ground truth they're being predicted compared against, right? This goes into solution conditions, etc. So what type of information when you're trying to predict an ensemble about the experiment do you need or do you want, or have you already integrated into your algorithms in order to predict the ensemble that you're actually getting compared against? So I think this is a question directly for any predictors of ensemble methods right now.
Yeah, and it actually is a really good point. Like if we consider the protein A experiment, I don't think we talked about the conditions in the spec, right? Bruce had, and Terry. And certainly when people do modeling of the two-state systems, the conditions are not available to them. So the degree to which conditions alter populations or even the states themselves, the predictors are blind to that at the moment.
The question for us was answered by the conditions that were given in the paper that reported the wild type CDIO. So formally they were there, but they weren't specified in the actual specifications document that we sent to CASP. So it's a good point. We should have specified the pH, the ionic strength of the solution, and the temperature. All of those presumably are pretty important variables, at least to some of the methods that were used to predict.
Well, I guess it's also still an open question in a way, right? As an experimentalist, I would love to think that all my conditions I try really hard to perfect are important. But has any predictor actually seen their methods improve when they take into account ionic conditions or something? Or as of now, is our prediction capability such that we don't necessarily need those for prediction?
We've had some success with predicting salt dependency of similar systems, so chain compaction for these multi-domain proteins. So knowing, for example, the salt concentration, would be useful for us.
I mean, for protein ligand stuff, if you screw up the protonation state, that's a good recipe to not get a good prediction. Not that getting it right with this would get you.
I see another question right here.
Yeah, no, concerning the same, I think that the way that we validate is fundamental. It would be nice to know that beforehand. So we know, for example, if the ionic concentration or something like that is going to play a role. I mean, maybe you can make many models with different ions or something like that and then find no difference. So I think that first to know how they are going to be measured and compared.
Preston?
So, in the interest of time, I'm going to wrap it up now, but I'm going to one or two more questions of people who want to say anything on this general topic. Did I hear something online? Was somebody going to say something online? On the Zoom?
No, I'll do it in chat.
Okay. One or two more questions or comments? Wei Zhang, you've been wanting to say something. Go ahead, and then Susan. Go ahead.
So I want to say something about the rule of CASP. Maybe in example category, we can tell more information about or describe the protein states or the states of each target. For example, we have two targets, one target like V1, V2. We can give some additional information to tell the predictor this target has some like which state or same side or different side or something information, because we found as the guy mentioned in his assessment, he has some difficulty to assessment the correct model submit the predictor. We also find some difficulty when we modeling the target and submit the model to which like V1, V4 or V1 or V2. So I guess maybe next CASP, we can have some clear rule, let the predictor submit the correct state to the experimental structure, yeah, something.
And I think for the last comment or question, so Susan.
The reason why our beamline participates in CASP is that the atomic models are really important to us, because only with the atomic models can we generate mechanistic hypotheses that are testable and also understand better, say, for example, disease mutations that are not going to active sites or binding interfaces, but are sort of obscurely in the middle of the protein. It's these conformational changes that we think they're hijacking those changes. And so this is my plea to the community that for mechanistic understanding of these proteins, we really need the atomic models that match the experimental data.
Okay, well, that's a good closing comment. And so I think we should now thank all the participants in this ensemble session and for doing a great job and teaching us a lot of new things. So thank you very much, everyone. I think that we're going to turn the Zoom off. Is that right? Or we end the Zoom session now for this final wrap-up session? So thank you, everybody, for joining us remotely as well. And thank you, Terry, for organizing that session and doing a great job. Thank you very much.